Hey class, chapter 4, exponents and exponential variation. We're going to explore this problem in class. Here's our objectives. We're going to learn how to calculate values of expressions with positive and negative integer exponents. We're going to learn to raise positive and negative basis powers, to understand and use laws of exponents, and to use scientific notation. Those will be our 4 lessons. From this, today we're going to just try to understand a little bit more what exponents are. So we'll start here, just kind of getting to know what an exponent is. Some terms that you need to know. The 2 is called the base, the 3 is called the exponent, and when you write it as 2 to the third, that's exponential notation. Now, that the exponent 3 tells us how many times to multiply that base. So it's equivalent to this. When we write it like that, that's called expanded form. And that has a value. 2 times 2 times 2 is 8. That's called the standard form, or standard notation. So here we have exponential notation, 5 to the 4th power. What that means, expanded form, and the actual value of that is 625, and that is standard. All right, so let's do a couple problems here. It says write p times p times p times q times q using exponents. So the exponent really just tells us how many times we are multiplying that factor, each factor. So we're going to write this as p to the third. And it's times, and then we have 2 factors of q, so we can write q to the second. But in algebra, whenever we're doing multiplication and we have all variables, we do not use any symbol to show that. So we just write p to the third times q to the second like that. So really, just count the number of times you're multiplying by that factor. 7 is the base. 6 is the number of times we're multiplying by 7, and that's exponential notation. Here we have m's and n's. We can regroup those so that we have the m's together using the commutative property. And so we get m to the second times n to the 4th. And again, when we're doing algebra, we don't use any operation symbol. So we just say m to the second times n to the 4th, like that. All right, so we're going to count up the factors of x. Again, we could rearrange these, but we know with the commutative property we can group all the x's together and all the y's together. So we see that there's 3 factors of x, and we see that there's 4 factors of y. So we're going to write x to the third, y to the 4th power. Now, just a little note here, any non-zero number to the 0 power is 1. And you can check that on your calculator, and I'll show you how to do that. But 25 to the 0 power is equal to 1. 7 to the 0 power is equal to 1. And amazingly, 100,000 to the 0 power is equal to 1. I think this is a good time to learn how to do exponents on our calculator. So, and also to show that your calculator thinks any number to the 0 power. Now, for calculating exponents, we're going to use this button right here. It's called the caret key. Unless it's a second power, we can use that button there. So if I was doing 4 to the second power, I could just use the squared button. Press enter, that's 16. And remember, that means 4 times 4. Same thing. If I am doing a higher power, like the 4th power, say 7 to the 4th power, I use the caret key. And remember, that just means 7 times 7 times 7 times 7. Same thing. Okay. Now remember, we just discovered that any number to the 0 power is 1, so I'll just show that. As long as it's a non-zero number. Anything, 25 to the 0 power, 0.5 to the 0 power. I even said 100,000 to the 0 power would be 1. And it also said that the base can't be 0. So 0 to the 0 power just doesn't work. Your calculator doesn't know what to do with that. And we'll talk a little bit more about class why that is. But all right, so let's do a few more problems. Now that we have our calculator, we know how to use it. So here in example 2 says evaluate 6 to the second. That one you can do without a calculator, and you know that just means 6 times 6, which is 36. 4 to the third power, if I expand that, I get 4 times 4 times 4. And if I go ahead and use my calculator to figure out what that is, look at this, 4 to the third power. That's 64. So 4 times 4 times 4 is 64. 2 times 2 times 2 times 2 times 2. That one we should be able to do without a calculator. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32 in standard form. 5 times 5 times 5, that is equal to 5 to the third power, 125. All right, let's do a couple of these problems. So here we want to tell whether this statement is sometimes true, always true, or never true for positive integer values of n. If a statement is sometimes true, state for what values it's true. So I think we're going to use our calculator to help with this. So basically what we're saying is, if we keep multiplying by 2, is there some power of 2 that is exactly equal to 2048? All right, I think the best way to do that is to just do powers of 2. Start with 2 to the first power, which is 2. Then multiply by 2. So now I have 2 to the second power, and I can just count as I go. 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, and there it is. So 2 to the 11th power is 2048. So it is sometimes true when n equals 11. How about 4 to the power? Is there some power of 4? Well, you might think there is, since doubling gave us 2048. Quadrupling, which is just doubling twice, might end up being a number like that also. So let's check on our calculator. Start with 4 to the first power, which is 4. Multiply by 4, so that's 4 to the second, 3rd, 4th, 5th, 6th. And you see that we just passed 2,000 by. So there is no whole number power of 2 that is exactly. So this will never happen. So, all right. Is 3 to the n less than 1,000,000? That is 3 to the n. This is the inequality that represents 3 to the n is less than 1,000,000. And we know it is for some values. I mean, if you put 3 to the first, that's equal to 3, so that's definitely less than 1,000,000. But we can use our calculator to find for how many values. Eventually, by multiplying by 3, we're going to pass 1,000,000. So I'm just going to go times 3, there's 3 to the second. Just keep hitting the enter button, third, fourth, fifth, sixth. This is 3 to the 6th, 3 to the 7th, 3 to the 8th, 9th, 10th, 11th, 12th, 13th. So 3 to the 13th, we are above. I just want to check to make sure I counted right. Yes, 3 to the 13th is the first time we're above 1 million. So sometimes, and we can say as long as n is less than 13. And an easier way to write that would just need to write n is less than 13. All right, is 0.5 to the n between 0 and 1? Basically what we're saying is when we keep multiplying by 0.5, and you can just think about this, so multiply by 0.5, so what we're doing is taking half of a half, or 50% each time. You can think about that, we're going to keep getting smaller, but when you take half of something, you're always left with something, so you're always going to be greater than 0, and we can use a calculator to show that. Start with 0.5 times 0.5. And so you can see that the number was cut in half, or it's 50% of the number, and every time we hit enter, it keeps doing that. But also notice that number is always positive. And as long as we're taking half of a positive number, we're going to end up with a positive number. So we can safely say that this always, for all n values that are positive whole numbers. All right, I think I'll stop there, and the rest of it we'll work on in class.